This is the second part of your DNA structure notes. So ignore the title. We'll get to Okazaki fragments here in a second. But what I want you to do is get a blank sheet of paper. I would probably turn it lengthwise. And let me get my pen. And I want you to draw this. All right, and you can pause the video whenever you need to. So I'm just gonna go ahead and tell you the directionality. So this is a strand of DNA that is getting unzipped. It's getting ready to be copied in synthesis during interphase. So I'm just gonna go ahead and tell you, I'm not gonna draw the nucleotides. I could, like we could draw the individual nucleotides, but I'm just gonna draw them as lines. So what I've drawn here is the sugar phosphate backbone. So this over here is the 5' side. Whoop, that was my dog, she coughed. And if you come all the way down, you trace it all the way down to the other side. Remember, this is therefore the 3' side. And because DNA is anti-parallel, right, across from the 5' side must be the 3' side. Follow this all the way, follow it all the way down. Didn't mean to draw that there. Is the 5' side. So we can right off the bat see that DNA is anti-parallel. The 3 and the 5' sides are opposite of each other. The strands that we just drew are the original strands. So let's go ahead and label that. Another name for that is template. And another name is parent, right? So these are all synonyms. So this is the original template or the parent strand that we just drew, right? Same thing on the bottom side. Let's also go ahead and add some nitrogenous bases. And you don't have to pick the same ones I'm gonna pick, but let's pick, let's do A, T, C, G, and whatever. Let's just do A, T, 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 C, C, G, A, T. I'm just putting a whole bunch of letters here, and that's probably good enough. All right, well, remember that DNA is complementary, so as we label the other side, the A must have been attached to a T, that must have been an A, that must have been a G, that must have been a C. Across from the A would have been a T, that would have been an A, that would have been an A G would have gone there, another G, C, T, A, T, C, G, A. So whatever letters you picked on one side, just make sure that the opposite side is complementary, right? Notice that here on the left, where the DNA is still attached to itself, there are hydrogen bonds between the T's and the A's. There's 2 of them. And remember, there were 3 of them between the C's and the G's. But they've been broken here on the right, and that's because helicase has broken the hydrogen bonds and unzipped this molecule. So let's go ahead and draw helicase. So I'm going to switch colors. I'm going to do my best to try and color code things. So let's say that our enzymes are in blue. All right, so here's helicase. And which way is helicase moving? Is it moving to the right or is it moving to the left? You can pause if you need to think about it. So hopefully you've paused. Helicase is moving to the left. Helicase has already unzipped everything over here on the right side, which means it's been there and done that. So it is progressing further to the left. Okay? Hold on, give me 1 second. I have to get my dog's ball under the dresser. Callie, you are crazy girl. All right, go get it. All right, let's add some more vocab. So I'm going to change color again. Let's go to purple. Helicase is always at what is called the replication fork. They call it the replication fork. It's like a split in the road. If you have a road that splits in two, that's called a fork, like a fork in the road. So that's why they call it the replication fork. It's just some extra vocab. All right. So DNA polymerase is the enzyme that's going to start to build our complementary strand. And when you build a complementary strand, remember, if we, on the top here, I'm going to redraw the sugar molecule. Remember that we had an oxygen at the top. Right? We had carbon 1, carbon 2, carbon 3, carbon 4, and then carbon 5 was like right there. Right? When you add bases together and you build that complementary strand, DNA polymerase can only attach new nucleotides to the 3' side. Only to the 3' side. So let's go ahead and add our, I'm actually going to go ahead and stay in purple here. Can I pick it? I don't want to pick green just in case anyone's colorblind. Let's do it in black, just because I'm kind of running out of colors. So black will be our complementary strand. So go ahead and draw a complementary strand here and a complementary strand here. And go ahead and label those. So those are complementary strands. All right. Complementary, complementary, and let's label the direction. So remember that DNA is anti-parallel, so opposite of the 3' side here, you've got a 5', which means that this was the 3' end down here. And then on this bottom complementary strand, opposite of the 5 is the 3'. So I don't know why it made that line. And then over here was the 5' end. Now DNA polymerase, remember, can only attach and build from the 3' side on the complementary strand. So let's get our blue back out. That means that DNA polymerase is going to attach, and we can just draw this big box, is going to attach to the 3' side on the original strand and the 5' side on the complementary strand. So on the top strand, on this top portion of this DNA molecule, it's going to be right here where I drew this blue rectangle. And it's going to move towards the left. In this case, it's going to follow helicase. Helicase is also going to the left. Right? So it's going to come here and it's going to say, oh, there's an A, I better put a T. And as it moves to the left, it's going to just add more bases. So it's going to put a C, a G, an a G, and you can go ahead and do this on your paper too. A T, and an A. And as helicase unzips the DNA, more and more exposed parent template original bases are available for DNA polymerase to make a complementary strand on. Right? So it's nice and easy on this top portion because DNA polymerase is following helicase. So helicase unzips the DNA and DNA polymerase follows right after it. It's super, super convenient and super easy. And if you want, you can draw the hydrogen bonds here as well. I'm just going to draw a couple. right? And remember, because you have to attach the nucleotides to the 3' end, there's no easy way to remember this. There just isn't. I'm sorry. You can think of the phosphate as being like blocking. So back up here in the top corner, top left, this phosphate is a big kind of block. It's preventing the enzymes from attaching anything to it. So I guess that kind of helps you remember. You have to attach your nucleotides to the 3' side, right? So on the complementary side, the 3' end is towards the left. That's why you're building towards the left. So on the complementary strand, you move from 5' to 3' in the direction of the 3' side. Since DNA is anti-parallel, it's the opposite on the original strand. So you're moving from the 3' side to the 5' side on the original strand. And we can work more on this in class. But the point is that DNA has to be built in the 5' to the 3' direction. So what we usually do is focus on the complementary strand in terms of that description. All right, on the bottom strand in this drawing, the 5' side is on the left. Here it is right there. So that is where DNA polymerase is going to park itself, and it's going to move. Again, it has to synthesize from the 5' side to the 3' side on the complementary strand. So in this case, it has to go away from helicase. It has to move away from helicase. So here's an A, it's going to put a T, then an A, then an A, then a G, then a G, then a C, then a T, A, T. A. All right, and it's going to keep moving to the right until there's just nothing left. So the difference here, and you might have picked this up, is that on this bottom strand, by the time that the DNA polymerase has made its way all the way down here to the finish line on the bottom right, helicase in the same amount of time has moved further left, which means there is a gap. There is exposed bases between DNA polymerase where it started over here and where helicase is now, which is like way off my screen to the left, right? So DNA polymerase has to unattach. It has to unattach from the DNA strand that it just made, catch up to helicase, and reattach. So it might be hard to visualize, and it is going to be hard to visualize virtually. But take my word for it. We can demo this in class, and I can show you when we all return in person at some point, perhaps, maybe or maybe not. But there are chunks of DNA that are synthesized on this bottom strand. If you can visualize it, great. If you can't, it's okay. Just go with me on it. These chunks that are synthesized in chunks, really is the best way to describe it, are called Okazaki fragments. The guy who figured this out was Japanese. His last name was Okazaki. That's why they're called Okazaki fragments. And you only get the Okazaki fragments on one of the two sides, right? And then the last thing is that we name those sides. So the side that has the Okazaki fragments is called the lagging strand. It lags behind. And the side that's honestly easier, where the DNA polymerase follows the helicase and doesn't have to make Okazaki fragments, that side is called the leading strand. And I'm going to post a video that I think might be easier to watch than this one that covers this too. I'm not going to test you on this material, but because you are honors, I did want to cover it. So I will say that again. I am not testing testing you on this drawing. However, because you're honors, we cover it. So I hope that eases some concerns. We'll hash this out more together. I hope this helped, and I will see you in class.